Good day, viewers. We are welcome yet again to our physics online review, where we are going to be looking at gas laws. A gas law is a very important topic in physics. We are going to be looking at various aspects, including the kinetic theory of gases, which will explain to us the behavior of gases. We are going to be looking at the various gas laws, starting from Boyle's law to Charles' law to the Precious law, which I can also call the Gay-Lussac's law, the Precious law. And we are going to be looking at the general gas law, a combination of all three gas laws, the general gas law or the general gas equation. And lastly, we are going to be looking at the measurement of the pressure of a gas pressure measurement, gas pressure. And we are going to be solving some questions to further exemplify the topic. I hope we have an interesting time together. So first, we are going to try to look at the behavior of gases. There's a particular concept in which the behavior of gases have been completely highlighted into, and that is what we call the kinetic theory of gases. And there are statements under the kinetic theory of gases that will make us understand perfectly how gases behave. Number one, among the statements of the kinetic theory of gases is that a gas system consists of large number of particles which collide elastically with each other and with the walls of the container. If you have gases in a container, what you are actually referring to gas are things made up of large number of particles, and those particles, due to their constant random motion, are constantly hitting each other, colliding each other, and colliding with the walls of the container. They are colliding elastically with the walls of the container, and we have already explained elastic collision under Newton's law. I want you to refer to our lesson on Newton's law of motion to properly understand how collision can be elastic and inelastic. But gas molecules collision with each other and with the walls of the container are elastic. That's the first statement of the law. Number two, gas molecules move in continuous random motion. Gas molecules are continuously moving. There's never going to be a time where gas molecules will be found still. There's never going to be a time where gas molecules will be found still. They are continuously moving across the body of the container, even outside the walls of the container, if it is not covered. So gas molecules are constantly moving and they exhibit high-speed random motion. High speed means they move very fast and they move randomly. That's the only type of motion that they undergo. They move without any specific pattern. Number three is that the actual volume of gas molecules occupied, the actual volume of gas molecule is negligible compared to the volume of the container. The actual volume occupied by gas molecule is negligible. Anytime you put gases inside a container, they will immediately fill up that container. That is one thing about gas. They will immediately fill up the container. But if it were possible for us to pick the molecules one by one and bring them together to see the actual volume that they occupy, we will discover that the gas that elsewhere look as if it has filled the whole of the container actually occupy a small part of the container. The volume occupied by gas molecule is negligible compared to the volume of the whole of the container. And the last part of that law is that gas molecules have negligible force of attraction or repulsion between each other. Gas molecules, the intermolecular force of attraction or repulsion between gas molecules are negligible. That means the motion of a molecule is completely independent to that of the other because there is no form of attraction or repulsion that exists between the two of them. The four statements that I have explained make up what we call kinetic theory of gases, and it helps us to understand how any gas system behaves. Number one, that a gas system actually consists of large number of tiny particles that collide elastically with each other and with the walls of the container. The other part is that gas molecules exhibit constant high-speed random motion. The third is that the actual volume occupied by gas molecule is negligible compared to that of the container. And the last is that there's a negligible intermolecular force of attraction or repulsion between gas molecules. With this said, I must let you know that anytime we have a gas system, there are three properties that are peculiar to those gas systems. There are three properties that are peculiar to the gas system. Those properties are the volume of the gas, the temperature of the gas, and the pressure of the gas. These three are the properties of every gas system. Any gas system is kept at a particular volume because of the prevailing temperature and the prevailing pressure. If either of the two changes, definitely the third will also change. So every gas system is operating at a particular volume, at a particular temperature, and at a particular pressure. If you decide to change any one of these three qualities of gases, the other two must also change. The change will be reflected in the other two. Now, I must tell you the properties of gases that we have so outlined. There are several things within the gas that each of them depend on. For example, the volume of every gas system directly depends on the intermolecular spacing of the gas system. The intermolecular spacing. When I say the intermolecular spacing, I'm actually referring to the average spacing that exists between a molecule and the other in every gas system. The space between one and the other, the space between a molecule and the other, the space between a molecule and the other. Of course, there's no fixed space between them, there's no fixed spacing between them, but we can actually find the average spacing of the average intermolecular spacing of every gas system. Usually, we'll discover that where a gas system has large volume, the spacing between the particles will be large also. But if it is possible for us to reduce the volume of the gas system, if it is possible for us to reduce the volume of the gas system, we will see that the space now available for the same number of particles that we had before must have been reduced. So, therefore, the intermolecular spacing will also reduce. So larger intermolecular spacing imply larger volume on the part of the gas, while smaller intermolecular spacing imply smaller volume on the part of the gas. Where the gas volume is reduced, we can by extension say that the intermolecular spacing will also be reduced. Where the gas volume is increased, we can by extension also say that the intermolecular spacing will also increase. Now, the pressure of the gas. Gas pressure depends directly on the frequency of collision. Gas pressure depends on the frequency of collision of gas molecules with the walls of the container. The frequency of collision of gas molecules with the walls of the container, If gas molecules collide with the walls of the container frequently, then we expect the gas system to have a very high pressure. It means the pressure of the gas system is large. If the gas molecules collide with the walls of the container frequently, it means the pressure of the gas system is very, very high. But if the gas molecules do not have very high frequency of collision with the walls of the container, probably because it is taking them longer time to get to the wall, they will say that the frequency of collision is low, and indirectly we are trying to say that the pressure of the gas is also low. So we are going to see how these two can affect each other, but let us look at the third one, the temperature. The temperature of every gas system is a direct function of the average kinetic energy of the molecules that make up the gas. Where they move faster, it means the temperature is high. Where they move slower, it means the temperature is low. Increase the temperature of any gas system, then the molecules will start to move very fast because they must have acquired kinetic energy to do so. Reduce the temperature of any gas system, then the molecules will start to move a little bit slowly because you have reduced the kinetic energy that they have to move. So temperature is directly related to the average kinetic energy of the gas system. Temperature is directly related to the average kinetic energy of the gas system, just as the volume is directly related to the intermolecular spacing of the gas system, and the pressure is directly related to the frequency of collision of the gas molecules with the walls of the container. Now, that said, now that we know the kinetic theory of matter, we know the three properties of matter: the volume, the temperature, and the pressure, and things that they directly depend on, we can now move on into examining the laws one after the other. So the very first one we are going to look at is the Boyle's law. Boyle studied the relationship between the pressure of a gas system and the volume of the gas system. I was able to give us a law that expressed the relationship of one. If there are three properties in a gas system, and we need to examine the relationship between any two, then it means we must keep the other one constant. If there are three properties in a system, and we need to establish the relationship between any two, the third must be kept constant. Wherever I need to establish a relationship between the volume and temperature, it means the pressure must be kept constant. And if I need to examine the relationship between the pressure and the volume, I must keep the temperature constant. So what Boyle did was to examine the relationship between the pressure and temperature, so the pressure and the volume. So obviously, he had to keep the temperature of the gas system constant. We want to see how the two of them will relate to each other if the third is kept out of that picture. And he was able to give us a law that is now famously known as the Boyle's law. Boyle's law states that the volume of a fixed mass of gas, is inversely proportional to the pressure, provided the absolute temperature is kept constant. The volume of a fixed mass of gas is inversely proportional to the pressure, provided the temperature is kept constant. In that statement, I've stated the law from the volume to the pressure. I can also state it from the pressure to the volume. It's still all the same thing. I can say that the pressure of a fixed mass of gas is inversely proportional to the volume, provided the temperature is kept constant. Mathematically, therefore, Boyle's law can be represented as pressure is inversely proportional to the volume, or the volume is also inversely proportional to the pressure. Either of the two will be very correct. If this is the case, we can change our proportionality to our equality. If you are going to do that, you must introduce a constant of proportionality on the other side of the equation. So you have P is equal to K all over V. K in that case must be equal to the product of P and V. So if the product of P and V is a constant, we can reproduce them within the equation. It means if I need to reproduce them, I will have P1 V1 must be equal to P2 V2. I said it in the topics that we have treated earlier, that anytime a set of quantity is equal to a constant in physics, you can reproduce that set of quantity. So if the product of pressure and volume is a constant, I can say that the pressure, the force pressure and the force volume, the product of the force pressure and the force volume must be equal to the product of the second pressure and the second volume. Where are we going to get the first and the second pressure and the first and the second volume? It simply means that if the volume changes from V1 to V2, it means that the pressure will also change from P1 to P2. Now, we have already seen that the two of them are inversely proportional. When quantities are inversely proportional in mathematics, in science generally, it means that as you increase one, the other one reduces. That's the meaning of inversely proportional. If pressure is inversely proportional to volume, it means as you increase the volume of the gas system, the pressure of the gas system is expected to reduce. And the reverse is also true. It means as you reduce the volume, the pressure will increase because the two of them are inversely proportional. If quantities are not inversely proportional, then are directly proportional. Direct proportionality implies that when you increase one, the other one must also increase. Now, we can be asked to explain the Boyle's law from the kinetic theory of gas. Remember that I said that the pressure of a gas system directly depends on the frequency of the collision of the gas system with the walls of the container. And I also said that the volume of a gas system directly depends on the intermolecular spacing, between within the gas system. So if I wish to prove this or explain this from the kinetic theory, I must be able to establish why an increase in pressure will lead to a reduction in volume, or why a reduction in pressure will lead to an increase in volume. I can also go from volume to pressure depending on whatever I think I can work with very well. Now, if we have the volume of a system of gas, let us assume that the cover of that system is movable, such that I can use this plunger, I can drive this plunger into the system, I can drive it out. I have gas particles enclosed within this system. If I decide to, so there's a particular volume that this gas particle has. There's a particular volume that it has, and because there's a particular volume that it has, we expect it also to have a particular degree of intermolecular spacing between one molecule and the other. We understand that it should have a degree of intermolecular spacing. If we decide to reduce this volume by pulling in the plunger, if we decide to reduce this volume by bringing down the plunger such that we now have the system, this represented, so clearly, because we still have the same number of particles, we now expect that the spaces available within them will have reduced. The spaces available within them, now that they have a lower volume, now that the volume has been reduced, the intermolecular spacing will also have reduced, because the volume is directly affected by the intermolecular spacing, or the intermolecular spacing directly affects the volume. So when we reduce the volume of a gas system, the intermolecular spacing will also reduce. And because the intermolecular spacing reduces, we expect that there will be higher frequency of collision with the wall of the container. Erstwhile, we expect that the intermolecular spacing will also affect the distance between each particle and the wall of the container. So there's a degree of frequency of collision that they will have before the pressure was reduced. Now, before the volume was reduced. Now that we have reduced the volume, we expect that the particles are now closer to the walls of the container. And because they are closer to the walls of the container, it means there will be an higher rate of collision of the particle with the wall of the container, with the walls of the container. There will be a more frequent collision of the particle with the walls of the container, and that ultimately leads to an higher pressure. So if I'm asked to explain this from kinetic theory, I will simply make sure that I mention these four very valid and important points. Lower volume means lower intermolecular spacing, and lower intermolecular spacing means higher frequency of collision. Higher frequency of collision of the gas molecule leads to higher volume, and that is exactly what Boyce was trying to tell us with the law. By saying that the pressure and the volume are inversely proportional, it means as we reduce one, we will increase the other. Now I've been able to show that as we reduce the volume, the pressure of the gas system must definitely increase. So the next thing we have to move into under Boyle's law is to try to see the graphical representation of the law. In what way can we represent the observation of boys graphically. We can decide to show the pressure against volume. If we plot the pressure and the volume, what is the diagram that we are going to get? If we plot the pressure against the inverse of the volume, or we plot the volume against the inverse of the pressure, what are we going to get? And lastly, if we plot the product of the pressure and volume against either of volume or pressure, what are the things that we'll get? Because they are inversely proportional, when parameters are inversely proportional, if we plot them directly, we are expected to get a curve. We are expected to get a curve when things are inversely proportional to each other. If you plot them directly, you are going to get a curve. It is not only for pressure and volume alone. That applies to any two quantities that are inversely proportional to each other. Now, if they are inversely proportional, a way to get a straight line between them is to plot one against the inverse of the other. If they are inversely proportional, it means that I can get a straight line out of the problem by just plotting one against the inverse of the other. Because if pressure is equal to kV, I can say that pressure is equal to K, open brackets, 1 all over V. So now, it looks as if pressure being inversely proportional to volume, I can say it is directly proportional to 1 all over volume. And because it is directly proportional to 1 all over volume, if I plot pressure against 1 all over volume, I should have a straight line that will start from the origin. And the same thing should go for volume against the inverse of pressure. Now, I've already told you, and that was what we derived, that whatever the pressure value could be, or whatever the volume value could be, the pressure, the product of pressure and volume must always be constant. So if at any time you plot anything, either volume or pressure, against the product of pressure and volume, you are not expecting the product to change. It is always a constant, irrespective of the value of the volume. So this is how this graph will be so represented. So if we want to represent Boyle's law, these are the ways by which we can represent it graphically. We'll leave Boyle's and we'll move on to the next law, that is Charles' law. Charles' law states that the volume of a fixed mass of gas, is directly proportional to the absolute temperature, provided the pressure is kept constant. I'll go through that again. The volume of a fixed mass of gas is directly proportional to the absolute temperature, provided the pressure is kept constant. I'll go over it the last time. I said Charles' law states that the volume of a fixed mass of gas is directly proportional to the absolute temperature, provided the pressure is kept constant. Provided the pressure is kept constant. When you are stating Charles' law, you must make sure that the temperature is absolute. That is temperature that has been converted into its absolute unit. An absolute unit of temperature is either Kelvin or Rankine. But in this part of the world, we use more of Kelvin. So we appreciate that you take your temperature to Kelvin. So anytime you are solving any problem on Charles' law, you must be very sure that you are using temperature that is in Kelvin. Most of the time, the question always like to confuse you by providing the temperature value in degrees Celsius. All you just need to do is simply to change from Celsius to Kelvin. So I can now continue. I'll say that the volume is equal to KT. It means that K, the constant, must be equal to V all over T. And I told you if any combination of quantity is equal to a constant, then we can reproduce that combination. So we have V1 all over T1 is equal to V2 all over T2. If there's a third condition, I can also say that it will be equal to V3 all over T3, because this law has showed me that the relationship between volume and temperature is direct. If the relationship between two quantities are direct, it simply means that and you increase one, the other one will ultimately increase. When I increase the temperature of the gas system, the volume of the gas system is expected to increase as long as the pressure is constant. So, how can I explain this from the kinetic theory? Remember that I said the volume is affected by intermolecular spacing of the gas system, while the temperature is affected by the average kinetic energy of the gas particles. The higher the average kinetic energy of the gas particles, the higher the temperature. The higher the intermolecular spacing of the gas system, the higher the volume. So, and I need to show that the temperature, when increased, will lead to an increase in the volume. If I have a gas system whose plunger is movable, the cover is movable, I have particles scattered across, I have gas particles in the system. These particles are held at a particular volume because they have a certain degree of intermolecular spacing that exists between them. These particles also have a particular temperature, so there's a particular kinetic energy or the average kinetic energy that I can say that the particles are moving with. If I suddenly heat this system, if I heat it, of course, the temperature will immediately increase. When the temperature increases, it means the kinetic energy of the particles will also increase because temperature will directly affect the average kinetic energy of the system. Once the kinetic energy of the particle increases, they start to move faster. They will start to move faster. Once they start to move faster, because kinetic energy is the energy that is associated with motion, they start to have higher velocities to move faster. One thing by which that can be done, if I want to now maintain the same level of, if I want to now continue, what will happen is that the fast moving particles will now exert a corresponding amount of collision on the plunger. Now that they are faster, they have the energy to move the plunger. They have the energy to shake the plunger. And once that is done, we will expect that the spacing between them will start to increase and they will start to move the plunger up. When they move the plunger up, what happens is the volume, the intermolecular spacing will increase, and once that is done, the volume at constant pressure will also increase. What I'm saying in essence is this: if the temperature of a gas system is increased, if the temperature of the gas system is increased, the kinetic energy of the gas particle will also increase. The kinetic energy of the gas particle increasing will want to translate into higher number of collision. If the collision is to increase, that means the pressure will also increase. The pressure cannot increase because I want to keep the pressure constant. So if I want it to still maintain the amount, the same level of pressure that it has before heating, what I must now do is to move up the plunger so that there will now be more spaces for them, or more space for them to express themselves. When that is done, they will have higher intermolecular spacing and therefore they will have higher volume. I'll go over that again. I said when you have a gas system, there's an amount of intermolecular spacing telling us that there's a volume that the gas system has. There's a kinetic energy that it has telling us that there is also a temperature that the system has. And there's an amount of collision with the molecules, with the walls of the container, telling us that there is a set pressure for this system. When I heat it, the temperature increases. The temperature increasing means that the kinetic energy of the system will increase. The first response is for the pressure to want to increase because now they are moving faster. When they move faster, it means that the first response is that the pressure will increase. But I want to keep the pressure constant. So the only way I can keep the pressure constant is for me to open up more space for it. If I open up more space by moving up the plunger, then the pressure will be restored, but what will now have happened is that I will have given more spacing to the particle, thereby increasing the volume. So anytime you increase the temperature, the volume will automatically also increase. What are the graphical representation of Charles' law? Charles, if we plot volume against temperature, because the two of them are directly related, we are expected to get a straight line. If we plot volume against temperature, because the two of them are directly related, we should get a straight line. The only condition for this to happen, though, is that the temperature is in Kelvin. Where the temperature is not in Kelvin, if you do so, if you plot volume against temperature in, for example, units that are not absolute units like degree Celsius, you are going to have a straight line, but the straight line will not start from the origin. Here, what we are trying to say is that when the volume is zero, if a graph is starting from the origin, it simply means that when the quantity that you have plotted on y is zero, the quantity you have plotted on x is zero. So when the volume is zero, the temperature is zero. But that is only correct if the temperature is in Kelvin. If the temperature is not in Kelvin, you will discover that at 0 degrees Celsius, the volume is not yet zero. It has a particular volume, but that is not zero. If you now want to get zero on this scale, you need to stretch the graph backward. If you stretch the graph backward, this point is a point where the volume will now be zero. And that point theoretically is minus 273 degrees Celsius. Minus 273 degrees Celsius. That's the point where the volume of a gas is theoretically taken to be zero. What Kelvin just did was to move the y-axis backward by adding 273 to all values. When you add 273 to this value, it automatically becomes the zero on the temperature scale, and then we can get a graph that is starting from, it's still the same point because 0 minus 273 is 0 Kelvin. It's still the same point. We are saying that the volume will be zero when the temperature is minus 273. Here too, the volume is zero when the temperature is minus 273, but now expressed in another unit. By adding 273 to minus 273, I was able to get the 0 Kelvin. This point is the origin for the Kelvin temperature. Now, the point where the volume is taken to be zero, the point where theoretically the volume of a gas becomes zero, is called the absolute zero of temperature. Absolute zero of temperature. It is the point where the volume of a gas is theoretically equal to zero. It is a point where there will be no thermal motion of any particle whatsoever, because all gases will have ceased to exist as gas at that particular temperature. It is not possible for you to have a gas that will still exist as a gas as minus 273, because at minus 273, based on this graph that we have, we expect the volume of the gas to be equal to zero. So it's possible that the gas will have turned to some other forms of matter like liquid or gas, but it will not exist as gas anymore, and it is called the absolute zero of temperature. At that temperature, the volume of the gas will be zero, the temperature of the gas will be zero. And that's why we call it the absolute zero of temperature. We move on to Pressure's law. Pressure's law can also be called the Gay-Lussac's law. There's another Gay-Lussac's law in chemistry. I hope we don't confuse it. Gay-Lussac gave us the pressure law, but there's another law, Gay-Lussac's law of combining volume. Please let's not confuse the two with each other. So I will just refer to this one as the pressure law. Boys studied the relationship between volume and pressure. Charles studied the relationship between pressure and between volume and temperature, while pressure law is studying the relationship between the pressure of a gas and the temperature of the gas. And it can be stated thus: the pressure of a fixed mass of gas is directly proportional to the absolute temperature. The pressure of a fixed mass of gas is directly proportional to the absolute temperature, provided the third quantity, that is the volume, remains constant. I will state that again. The pressure of a fixed mass of gas is directly proportional to the temperature, absolute temperature, provided the volume remains constant. If we are to re-express that, pressure is directly proportional to temperature. That means the pressure is equal to K multiplied by the temperature. That means K, which is the constant, must be equal to the pressure divided by the temperature. If K is equal to the pressure multiplied by the temperature, what we now need to do is to reproduce this expression that is equal to a constant. If we do that, we should have P1 all over T1 is equal to P2 all over T2. So if I know the first pressure and the second pressure, I can find one temperature from either the first or second. Now, how do I explain the pressure law from the kinetic theory? Remember that I said that pressure is affected by the frequency of gas molecules collision with each other, the frequency of gas molecules collision with each other and with the walls of the container, the frequency of collision, while the temperature is affected by the average kinetic energy. The temperature is affected by the average kinetic energy. If that is the case, we can continue with our gas system. We have a gas system with movable plunger. This time, we can even fix the plunger such that the volume remains constant. It is not possible for the volume to increase. So if we have a gas system, the gas system exists at a prevailing value of volume, temperature, and pressure, at a particular value of volume, pressure, and temperature. If I decide to heat it, the very first response is that the temperature will increase. If the temperature increases, the average kinetic energy will increase because the gas particles will now start to move faster. When they move faster, we expect almost immediately that at the same volume, the frequency of collision of gas molecules with the walls of the container will also increase. They will now hit the container more frequently. And if that is also the case, we expect the pressure to immediately increase because the pressure is directly related to the frequency of collision of gas molecules with the walls of the container. So once we increase the temperature, the kinetic energy, average kinetic energy of the particle increases, which at the same volume will lead to the frequency and higher or a more frequent collision of gas molecules with the walls of the container, which will also now lead directly to an increase in the pressure. If that is the case, we will say that we can now show a graphical representation of pressure and temperature. The graphical representation of pressure and temperature is exactly the same with what we had for volume and temperature under Charles' law, where your temperature is in Kelvin, the pressure in any unit, we expect a straight line that is passing through the origin, signifying that when the pressure is 0, the Kelvin temperature will also be equal to 0. But if you have plotted the pressure against the Celsius temperature, you still get a straight line, but not starting from the origin this time, such that if you extend it backward, you will be able to have a value that is slightly less than 0, which is minus 273 degrees Celsius. Minus 273 degrees Celsius is the point where the pressure of the gas becomes 0, according to this plot. So theoretically, as I said earlier, it is taken to be the absolute 0 of temperature, where we expect the pressure and the volume of gases to be equal to 0. That said, we move on to the general equation of a gas. When you combine Boyle's, the mathematical relationship that we have from Boyle's, Charles, and pressure law, you will discover that we can now write a more general equation that will now involve the three quantities that we are dealing with under gases, we will discover that if PV under Boyle's law is equal to constant, V all over T under Charles' law is equal to a constant, and P all over T under Pressure's law is equal to a constant. If I decide to merge this and this together, I should have what will look like PV all over T must be equal to a constant. So that can be reproduced. I can have P1 V1 all over T1 is equal to P2 V2 all over T2. That's a more generalized form of the relationship between these three parameters in a gas, where nothing is constant. Where nothing is kept constant, then the three of them will be expected to change, and we can now use this equation. If any one of them is constant, it will reduce to the respective equation. Now that is all about that. We can now move on to the last part of the topic, and that is gas measurement of gas pressure. Because what thing that will give us a little temperature of the three quantities that we are going to be using to solve for gases, pressure is about the only one that is going to introduce some minor challenges. Volume, of course, can be determined. You see that volume is given, or we are asked to determine it. If it is a fixed mathematical shape, then we can calculate its volume. Temperature, of course, there's no problem with temperature. The only thing that you can have with temperature is that its value may not be given in absolute terms, and you have to add 273 if you want to change from Celsius to absolute temperature in Kelvin. But pressure, the pressure of a gas can be much more. Now, we measure the pressure of a gas with what is called a manometer. Manometer can take different forms. I am going to try to explain a YouTube manometer. A manometer consists of a U-tube-shaped glass. If mercury is poured into the glass, you will see that you observe that the mercury will equally distribute itself along the two arms of the manometer. Why? Because the same pressure, which we refer to as atmospheric pressure, is acting at both ends, and they are equal. Atmospheric pressure is the pressure of the air. The air is in direct contact with this point, and it's also direct contact with the level of mercury in this arm. So the pressure that is exerted on the mercury on this arm is the same thing as the pressure that is exerted on the mercury on the other arm. If we now decide to connect one end to a gas system, let us say that we'll decide to connect one end to a gas system. It simply means that the pressure that is exerted on the mercury along this arm is now that of the gas, the pressure of the gas, while this open end still has the atmospheric pressure. For the purpose of this topic, we are going to be using P0 as our atmospheric pressure. When we connect this end to a gas system and this end is open to the atmosphere, we'll say that we have a manometer, a gas manometer, that can be used to measure the pressure of the gas. How does a manometer measure the pressure of the gas? By using the relative difference, between the height of the mercury along the two arms. If, for example, while connecting it to the gas system, we now observe that the mercury level in the arm closer to the atmospheric pressure, in the arm that has the atmospheric pressure directly on it, while is higher than the mercury level in the arm that has the gas pressure connected on it. What this is indirectly telling you is that the pressure of the gas is more than the atmospheric pressure. That is why the gas has been able to push the mercury against the atmosphere. That is why the gas has been able to push the mercury against the atmosphere. And in this case, I can be asked to find the pressure of the gas. I can be asked to find the pressure of the gas. What I will do is I will take the two levels of mercury in the 2 amp. Please listen and listen well. I'll take the level of mercury in the 2 amp. I will try to look for which of the two levels is lower. You start your calculation from the one that is lower. Which of the two levels is lower? Of course, let me call this point A and let me call this point B. Point A, of course, is clearly lower. I will trace out the corresponding level of mercury in the other arm. I'll trace out the corresponding level of mercury in the other arm. Let me call that point C. So once that is done, you are almost through with the important part. Now the difference in height. Remember that this is the higher level of mercury. I need to know again the difference in height between the two levels of mercury, the levels of mercury in the 2 amp. Let me call that H. I can easily use a ruler to measure it, the difference between the level of mercury in the 2 amp. If that is the case, I will now go back to my point C. I will tell them that pressure, all the substance above a particular point will exert pressure on that point. All the material that we have above a particular point will exert pressure at that point. 1. And 2, the pressure at the same level must be equal. The pressure at the same level must be equal. When you use those two, you'll be able to get anything. Number 1 that I said you should use is that the pressure at the same levels are equal. And number 2, all the materials or fluid or liquids that you have above a point must exert pressure on that point. So I'm going to start by saying point A, pressure at point A must be equal to pressure at point C. That's correct. Why? The two of them are at the same level. Please note, now that I know that pressure at point A is equal to pressure at point C, what is the item that is creating the pressure at point A? It is the only thing on A is the gas. So the pressure at point A is the pressure of the gas, while the pressure at point C, there are two columns of liquid or fluid acting on point C. Number 1, it has this height of mercury, because I have mercury all through. So there is this height of mercury that is directly above point C. So I want to find the pressure of that mercury, plus above that, because it is also open to the atmosphere, I have the atmosphere above it that is also going to exert the atmospheric pressure. So clearly, I can find the pressure of the gas by adding the pressure of the atmosphere to the pressure of the gas, to the pressure of mercury. The pressure of this height, just this height, is what you have above point C, the pressure of the height of mercury. Now, let me give you an example of a way by which this can be applied. If we have a U-tube manometer, that is connected to a gas, I'm going to now I'm going to use another form of this to explain. I have mercury all through the U-tube. The end that is closer to the end that has the gas pressure, the level of mercury along that arm is higher than the level of mercury that is connected to the atmosphere. What this is trying to tell us is that the atmospheric pressure is larger than the pressure of the gas. That is why the atmosphere is able to pushing the mercury towards the gas. Let us assume that this is given to me, the height of the mercury in the shorter arm is given to me to be 15 centimeters, while the height of the mercury in the longer arm is given to me to be 25 centimeters. One other thing, anytime you want to find the pressure due to a fluid, you need to know the density of the fluid, multiply it by the height, and multiply it by acceleration due to gravity. We are going to see this in one of our classes on pressure, and I hope you have the time to review what we said towards the derivation of this formula in the lesson. If I have a liquid on a particular platform, that liquid will exert a pressure on that platform. The pressure that the liquid is exerting on the platform depends on three things. What are those three things? It depends on the density of the liquid, it depends on the height of the liquid, and it depends on acceleration due to gravity. Please always remember this. It depends on those three things. So that is why generally, most of the time, they always express the unit of pressure as certain centimeter, I can say 15 centimeters of mercury. Yes, it is acceptable. What they are indirectly telling you is the pressure we are talking about here is the pressure that a column of mercury of height 15 centimeters, the pressure that it will exert. So you can now use this formula to change it back to the standard units. What is the density? You have to use the density of the liquid that is being referred to. That's density of mercury. If you need it, they will give you the height of mercury. What is the height of mercury? That is the height that comes with the unit, 15 centimeters. You convert it to meters, and obviously, acceleration due to gravity is 10. So when you see units of mercury, unit of pressure being expressed as millimeters of mercury, meters of mercury, please note that it is the pressure that they are trying to give you. Now we can move on. How do we find, so we want to get the pressure of the gas in this situation. How do we find the pressure of the gas? Please, what we'll simply do is, like I said here, look for the lower level of mercury in the 2-arm. Which level is the lower level of mercury in the 2-arm? Obviously, it is this. That's step 1. I'm going to call that point A. You can use any other letter. It's not compulsory. You use A. Now, find its corresponding level in the other arm. The corresponding level in the other arm, I can call it point B. Now, make sure you know the top level and the bottom point. Make sure you know the difference between them. The difference between, I hope you know that from the base to this point is 25. From the base, and that same base to this point is 15. So the difference between the height must be 10 centimeters. If it is 10 centimeters, I can now write my equation. The first equation you must write is that the pressure at the same level must be equal. Pressure at point A must be equal to pressure at point B. Now write out what are the things that constitute the pressure. The only thing that constitutes the pressure at point A is the thing above it, and that is the atmosphere. So pressure at point A will be the atmospheric pressure. What about pressure at point B? Pressure at point B will be obtained from those things that you have above B. And there are two things that we have above B. Number 1, we have 10 centimeters of mercury, and we also have the gas, the pressure of the gas. So I'm going to write the two. The pressure due to 10 centimeters of mercury plus the pressure of the gas. And mind you, I hope you know that it is the pressure of the gas that we are looking for. I will make it the subject of the formula. So the pressure of the gas must be equal to, you bring this to the other side, it becomes atmospheric pressure minus pressure due to 10 centimeters of mercury. If, for example, they give me atmospheric pressure to be 76 centimeters of mercury, then I can subtract this also from it, which is 10 centimeters of mercury. If I subtract the two, I should have 66 centimeters of mercury. I told you that the pressure must be less than that of the atmosphere because of the fact that the atmosphere has pushed the mercury level upward. So that is how to get the pressure in a manometer. We are going to review another aspect of gas measurement, and that is a barometer. Barometer is usually used to measure the atmospheric pressure. Manometer is used to measure gas pressure, while barometer is used to measure the atmospheric pressure. It's used to measure the atmospheric pressure. Now, How do we make a barometer? The liquid that we use for a barometer is also mercury. Mercury is one of the most important fluid for measurements in physics, in science, even in engineering. Mercury is one of the most important fluid. If you pour mercury in a basin and you invert a tube inside the basin, you invert a tube inside the basin. Now, I expect you to know that generally, if you have a drum, you can, if you take a cup, you place it inverted on the surface of water, if you take it down, if you press it down with your hand into the water, and if you then bring it out, you will find out that the inner portion of that cup is still dry as possible, telling us that despite the fact that the cup went into the water and came out, as long as it goes in straight and comes out straight, then water will not enter into it. Why? The simple explanation for that is there's nothing that is completely empty. So that cup is definitely not empty. While placed on the surface of water, it has air in it. If it has air in it, by the time you press it down, I hope you understand that the air remains inside it. And because air is matter, it has space, it has weight, and it occupies space. Any space that matter occupies, there's no other matter that can come in. You only have to find a way to remove that one first before another one can come in. And if you are going to do that, that is what you get. When you put the cup inside the water, if you hold it slanted, then some of the air will leave as bubble, then water will come in. If you keep it further slanted, more air will leave and more water will come in. So that is when you can now start to get water directly into the cup. That's when you can now start to get water directly into the cup. If you do the same thing for a test tube, of course, we will need a larger basin to accommodate the tilting of the test tube. When you tilt the test tube, more air will leave and water and mercury will come in. If we further tilt the test tube, more air will leave and water will come in. If we continue to do that, it is possible to completely try to evacuate all of the air inside this tube. It is possible to evacuate all of the air inside this tube so that the mercury will continue to fill it. But no matter how well you try to evacuate the air inside this tube, there is a limit to the height that mercury can go inside the tube. The maximum height that mercury can go inside this tube, let us assume it is represented as capital letter H, is a measure of the atmospheric pressure that is pushing the liquid into the tube. The maximum height that the liquid can go inside this tube is a measure of the atmospheric pressure, because it is atmospheric pressure that is acting on the surface of the fluid, mercury this time, that is pushing it into the tube. So wherever it gets to, ultimately can be taken to be the atmospheric pressure in the height of mercury. Usually, at normal condition, we expect it to be 76 centimeters, but it can vary slightly away from that value based on wherever you are on the surface of the earth. So if that is the case, we call this one a barometer. And what it has done for us is to measure the atmospheric pressure by simply expressing the atmospheric pressure in terms of height of mercury. If this is 76, it is never going to be possible for this mercury to move further inside the tube, even if the tube has been completely evacuated, because there's a limit to which atmospheric pressure can support a column of liquid. Beyond a particular value, it won't be able to support it, and the maximum height can be taken as the atmospheric pressure. Now, this is a barometer. If we are expecting the pressure based on the height of mercury inside this barometer to be 76 and it is less than 76. Let us assume that we're expecting a certain height, 76. I told you earlier that it is not all the time that the height will be 76. But if you are expecting a height of 76 and we have a value that is a little bit less than 76, we have a value that is less than 76. What that simply means is that this barometer is 40. And the main element in a 40 barometer is air that must have been exerting pressure at the top of the mercury level. If air has been exerting pressure at the top of the mercury level, then it will not allow the mercury that is filling this tube to get to the maximum height that we are going to use to determine the correct atmospheric pressure. So that air atop this tube, we can be asked to find this pressure. If, for example, I'm expecting the atmospheric pressure to be 76 centimeters of mercury, and here it is now reading 70 in length of mercury. Of course, it is 40. If it's not getting as high as 76, what I will do is simply to pick any point within the tube. I will pick any point within the tube just as I have done for a manometer, pick the point that is directly below, that is in the tube and is at the same level with the surface of the liquid in the basin. I can pick any point on the basin and I can pick any point in the tube that is at the same level with the basin. I told you that pressure at the same level are equal. If I call this point point A and I call this point B, what I'm indirectly saying is that the pressure at A must be equal to the pressure at B. If the pressure at A is equal to the pressure at B, the pressure at A must be equal to the pressure that is created by those elements that it has on top of it. And there are two elements that it has on top of it. I hope you can see that. Those elements that it has on top of it are, number one, this height of mercury, 70 centimeters of mercury, and the air that is also exerting a downward pressure on the surface of the mercury. So that will be, if I represent this as PA, that's the pressure of air plus the pressure due to 70 centimeters of mercury. Pressure of air plus the pressure due to 70 centimeters of mercury must be equal to the pressure of B. And the pressure at point B is just the atmospheric pressure, P naught. So I can now say that the pressure of the air that is left inside the tube, which is making our barometer 40, is equal to P naught minus P of that 70 centimeters of mercury. If that is the case, I can have pressure at point A is equal to P naught. What is P naught? 76 centimeters of mercury minus 70 centimeters of mercury. If we do that, PA should be equal to 6 centimeters of mercury. And that is how we always get the pressure exerted by air that is making a barometer 40. There are other forms by which the pressure of air can be given apart from those of a barometer or manometer. We can be given just a test tube. We can be given a test tube, but in three different orientations. We can be given a test tube that has used some drops of mercury to trap air. This is possible if the tube is very narrow, such that when you drop some amount of mercury, it will not get to the base because of the liquid or because of the air that is there. So we can have it in this orientation such that the open end is uppermost and the sealed end is at the bottom. We can have it horizontally. If we have it horizontally, such that the drop of mercury is also trapping certain air, just as we have it here. We can also have it inverted. It's possible we have it inverted. If that is the case, what we just do is we can be asked to find the pressure of the air if this is set under gas pressure. Of course, the only gas in this question is the trapped air. So if we are going to measure the pressure of anything, it has to be the pressure of the air that is trapped within the test tube, the pressure of the air that is trapped within the tube. Now, when the test tube is horizontal, because atmospheric pressure and air are at the same level, please just tell them that the pressure of air in the tube is equal to the atmospheric pressure in the horizontal orientation when it is placed horizontal. But when it is inverted in this form, it simply means that the pressure of the air must be equal to the pressure exerted on it by every item that it has. The pressure exerted on it by this height of mercury. Let me call this height of mercury as X, and the atmospheric pressure, because it is open to the atmosphere, P naught. The atmospheric pressure, it is open to the atmosphere, and that is P naught. So we'll say that the pressure of the trapped air in situations like this must be equal to the addition of all of the pressures of substances that we have above it. And that includes the pressure due to X centimeters of mercury plus the atmospheric pressure P naught. The pressure due to X centimeter and the atmospheric pressure P naught are what will create the pressure on the trapped air. In this situation, this is slightly different. Let us assume that the height of the mercury column is Y. What I can do here is I want to find the pressure of the trapped air, If I have to do that, I'll pick the lowest point inside this tube, and I'll also pick a point that is directly outside it. If I do that, remember that I said that the pressure at the same level are the same. If the pressure at the same level are the same, because B is a point external and open to the atmosphere, I expect the pressure at B equal to pressure at A. I expect the pressure at B to be equal to the atmospheric pressure, and the pressure at A to be equal to the pressure due to Y centimeters of mercury plus the pressure of the trapped air. So if I want to find the pressure of the trapped air in this situation, it must be atmospheric pressure minus pressure due to Y centimeters of mercury. So simply, what we will do anytime we have a system like this, if it is placed horizontally, the pressure of the trapped air is equal to the atmospheric pressure. If it is placed vertically, the pressure of the trapped air is equal to atmospheric pressure plus the pressure due to the column of mercury. If it is placed inverted, the pressure of the trapped air will be atmospheric pressure minus the pressure due to the column of the mercury. And with that, I think we can now try to see one or two questions to further explain the topic, to further simplify the topic. Number 1, a mass of gas occupies 20 centimeter cube at 5 degrees Celsius and has a pressure of 1.0 times 10 raised to the power 5 Pascal. What is its volume when its pressure increases to 1.5 times 10 raised to the power 5 Pascal with a rise in temperature of 20 degrees Celsius? So what we'll simply do in this question is to say that because both pressure, volume, and temperature are changing, so we'll use our general gas equation P1V1 all over T1 is equal to P2V2 all over T2. If that is the case, let us look at what we have been given. We are told that a mass of gas occupies 20 centimeter cube at 5 degrees Celsius. It occupies a volume of 20 centimeter cube. I will take that as my first volume. When the temperature T1 is 5 degrees Celsius and has a pressure of 1.0 times 10 raised to power 5 Pascal, it has a pressure of 1.0 times 10 raised to power 5 Pascal. What is the volume when its pressure increases to 1.5? What is now going to be its volume V2 when its pressure became 1.5 times 10 raised to power 5 Pascal? With a rise in temperature of 20 degrees Celsius. With a rise in temperature, T2 is a temperature of 50 degrees Celsius above the initial temperature. The temperature is now going to be 55 degrees Celsius. Mind you, for gas law problem, you are not expected to solve them in degrees Celsius. You have to convert to Kelvin. So my T1 must be equal to 5 degrees Celsius plus 273. That will give us 278 Kelvin. While my T2 must be 55 degrees Celsius plus 273. 55 degrees Celsius plus 273 will be 328 Kelvin. So if that is the case, I can now do P1 V1 all over T1 is equal to P2 V2 all over T2. If that is the case, my P1 should be 1.0 times 10 raised to power 5 Pascal multiplied by the volume 20 divided by T1. My T1 is 278. It must be equal to P2. P2 is 1.5 times 10 raised to power 5 multiplied by V2 is what I don't know that I'm looking for, all over T2. T2 is 328 Kelvin. So that I don't continue to carry large quantity of unneeded numbers, I can cancel out 10 raised to power 5 and 10 raised to power 5. I can now make V2 the subject of the formula by cross multiplication. V2 must be equal to 328 multiplied by 20 multiplied by 1 multiplied by 20 multiplied by 1, and I'm going to divide it by 278 multiplied by 1.5. If I do that, my V2 should be equal to 328 times 20 divided by 278 divided by 1.5. 15.73. 15.73 centimeter cube. So we move on to other questions. The setup illustrated is a setup that has been given to us. The setup illustrated in the figure below shows a capillary tube of uniform cross-sectional area. The drop of mercury is 15 centimeters. The dry air in one part is 30, while in the other part is 45. Here the dry air is 30 centimeters, while here it is 45 centimeters. We are told that this is the dry air, and we are told that this is the mercury. So the setup illustrated in the figure above shows a capillary tube of uniform cross-sectional area in two different arrangements. Using the data in the diagram, calculate the atmospheric pressure. Using the data in the diagram, calculate the atmospheric pressure. Since it has a uniform cross-sectional area, let me label it as A, and let me label these two as A. When shapes have uniform cross-sectional area, don't forget that we can find their volume as area times height, their volume or the volume of any part of it. So I can find the volume of the dry air in the first situation. The volume of the dry air in the first case is the area A multiplied by the height. The height in this case is 30. That is A multiplied by 30. 30 is the height of the air. It's only the air that I need to find the volume of. I'm solving this question under gas law, and it's only air in this question that is a gas. This V1. My V2 will be similarly 45A. That's the area multiplied by the height. Now I need to get the P1, the pressure of the air, the pressure of the trapped air in this case, not the pressure of the liquid, not the pressure of the atmospheric pressure, but the pressure of the air, because I want to solve this question as gas law, and air is the only gas that is here. Mind you, the volume that I'm going to use are for the air, so the pressure must also be for the air. The pressure here, in this situation, I'm going to call it P1. How do I get P1? P1 is simply going to be what I said it will be while we're treating test tube with trapped air in different orientation the last time. I said in this type of situation, you are going to add the pressure of the 15 centimeters of mercury plus the atmospheric pressure. Let me simply express this simply as 15 centimeters of mercury plus the atmospheric pressure, also to be expressed in the same unit. I don't know the atmospheric pressure. That is what they want me to find. Here, remember that I said when the test tube is inverted, the pressure of the trapped air, which is going to be our P2, will be equal to the atmospheric pressure, P0, minus the pressure due to this 15 centimeters of mercury. 15 centimeters of mercury. We are told that it is at the two arrangements are at the same temperature. So we'll just use our Boyle's law, which is P1 V1 is equal to P2 V2. Our P1 is 15 plus P0. Our V1 is 30A. It must be equal to our P2. Our P2 is P0 minus 15. And our V2 will be 45A. If we cancel out our A values, we will have, if we break the bracket, we should have 450 plus 30P0 must be equal to 45P0 minus 45 times 15. 675. 675. If we collect like times, we bring 675 here and bring 30 here. What would that be? 450 plus 675 is equal to 45P0 minus 30P0. If that is the case, I will have 15P0 is equal to 450 plus 675 should be 1,125. 450 plus 675 is 1,125. Therefore, our P0 must be equal to 1,125 divided by 15. If I do that, I should have 75 to be expressed at 77 centimeters of mercury, since I have decided to add it to the value expressed in centimeters of mercury. So we'll move on with more questions. Helium is a light gas and is usually used to fill weather balloons. It is often observed that the volume of the spherical balloon expands to a radius of 1 meter when the gas is heated by the sun in the day, 32 degrees Celsius. The material of the balloon is fully expandable and the balloon hovers at a constant height above the ground. Thus, the pressure of the gas can be assumed to be constant. calculate the radius of the spherical balloon at night when the temperature is 24 degrees Celsius. We have helium balloon during the day when the temperature is said to be 32 degrees Celsius. We have that same helium balloon at night when the temperature is said to be 24 degrees Celsius. We are told that during both periods of the day, it is hovering around the same height. So we can say that since it's having the same height, it's at the same level, and pressure on it in both cases are equal. So we will assume that the pressure is constant. We are told that the radius during the day is 1 meter. The radius of this spherical balloon during the day is 1 meter. What we need is the radius at night, and this can easily be done. We can find the initial temperature, which is the temperature at the day. That will be 32 plus 273, and that will be 305 Kelvin. We can find the temperature at night. That will be our T2, and that will be 24 plus 273. 24 plus 273 should be 297 Kelvin. We can now find the volume, because once the radius is given and we are told that it's spherical, then it will have volume. The volume should be pi 4/3 pi r cube. We don't have any problem because r is 1, so I can just say that it's 4/3 pi 1 cube, and pi 1 cube should be 1, so this should give us 4/3 pi. For the other part, I'll call this V1. For the other part, the radius is not given. I'll use the same formula since it's still spherical, pi r cube, and I'll leave it like that. So because the temperature and the volume are changing, I can now use the Charles law. The pressure remains constant. So I'll say that V1 all over T1 must be equal to V2 all over T2. My V1 must be 4/3 pi divided by my T1, 305. My V2 should be 4/3 pi r cube, and I must divide it by T2. T2 is 297. 4/3 pi should cancel 4/3 pi. So we have 1/305 is equal to r cube divided by 297. So I can find r cube as 297 divided by 305, and r must therefore be equal to cube root of 297, divided by 305. That should give me the answer to my r. It is 0.991. 0.991 meters is the answer to the question, and that is all about that. We'll take more questions. Now, we continue. We are told here that a glass tube in the shape of letter J. There's a glass tube in the shape of letter J. Has a shorter limb sealed. The shorter limb is sealed, and the longer limb is open. The longer limb is open. Mercury is poured into the tube until the level in both limbs is the same when the tube is vertical. Mercury is poured into the tube until the level in both limbs is the same when the tube is vertical. In this position, the length of air column in the sealed limb is 6.3. Of course, there will be air in the sealed part of the tube, and we are told that the height or the length is 6.3 centimeters in this position. More mercury is then poured into the tube until the length of the trapped air is 4.2 centimeters. So now in the second situation, more mercury is now poured until the length of air is now 4.2 centimeters. I guess that's correct. 4.2 centimeters. Calculate the difference in the level of mercury in the limbs. Calculate the difference in the level of mercury in the limbs if a mercury barometer reads 76 centimeters and the reading on a nearby thermometer indicate no change in temperature. The temperature has not changed and the barometer that is placed nearby is reading 76 centimeters. If you are given the reading of a nearby barometer, they are indirectly giving you the atmospheric pressure. And they said it is 76 centimeters of mercury. One other information that we are also giving here is that the reading on a thermometer that is placed nearby has also not changed during the course of this observation. That means the thermometer is also constant. If we know that, then we can now continue. Now here, when the length of the air column is 6.3, the level of mercury in both limbs are the same. The level of mercury in both limbs are the same. The level of mercury in both limbs are the same. But now we expect that the level of mercury is smaller, shorter. That means the level of air is now smaller and shorter. The meaning is air has now taken less volume. When it has taken less volume, we expect its pressure to have increased. When its pressure increases, we should see that by the fact that there will not be a differential, there will not be a difference between the height of mercury in the two arms. At this point, the level was equal. Now at this point, we expect the pressure of the air to be more. How are we going to show that the pressure of air is more? It has to be by the difference between the level of mercury in the two arms. So this is the difference. So we are asked to find the difference in the height of mercury in the limb. What's the difference in the height of mercury in the limb? What we will do, this is the level of mercury in this limb. This is the level of mercury in the other limb. The difference in the height of mercury in the two limbs is what they want us to find. Atmospheric pressure is given to be 76 centimeters of mercury. The very first thing I should do is I will try to come here and find and express the volume. I expect this tube to have constant cross-section. If it has constant cross-section, I can find the volume of the air. The volume of air that in the sealed limb will be area A multiplied by height 6.3 centimeters. In the sealed limb, the volume must be equal to area A multiplied by 4.2 centimeters. Now, the pressure. Because the level of mercury in the limb closer to the air and that closer to the atmosphere is also the same. The levels are the same. I expect the pressure exerted by the air in the closed limb to be equal to the atmospheric pressure because both of them are at the same level. If I call this point A and I call this point B, I can say that the pressure at point A must be equal to the pressure at point B since the two of them are at the same level. What is the exerting pressure at A? The air. What is the exerting pressure at B? Atmosphere, P0. So the pressure of the air in this case, which will be P1, will be the atmospheric pressure, which will be 76 centimeters of mercury. But here it is not going to be that simple. I will look for the shorter of the level of mercury in the two arms, and this is it. I'll call it point A. I'll find its corresponding height in the other arm, this will be my point B. I will start by saying that pressure at A must be equal to pressure at B. The only thing that I have on A is the air for which I'm finding the pressure, while the thing that I have on B are H centimeters of mercury and the atmosphere, the atmospheric pressure. So that should be the atmospheric pressure plus pressure due to H centimeters of mercury. Atmospheric pressure is given to be 76, and this is H. Both are in centimeters of mercury, and that will be my P2. In this situation, my P2 will be 76 plus H centimeters of mercury. And I can now use my Boyle's law to solve the two of them. So I should have P1 V1 is equal to P2 V2. My P2 has the element that I'm looking for. I'll say that P2 is equal to P1 V1 all over V2. My P2 is 76 plus H. My P1 is 76. My V1 is 8 times 6.3. My V2 should be 8 times 4.2. If I cancel out A and A, I will have 76 plus H is equal to 114. My height, therefore, will be 114 minus 76, and that should clearly be 114 minus 76. That is 38 centimeters, and that will be the answer to that question. We will now take our very last question under this topic. It also requires a diagram. I have a bit. That is what we have. There is a mercury thread. This is mercury. We have trapped air. This, of course, is a thermometer. And we have a water bait. This is a glass bulb. Now we can continue. We are told that a glass bulb connected to a U-tube manometer is placed in a water bait as shown above. The glass bulb connected to a U-tube manometer is placed in a water bait as shown. When the temperature of the water bait is 30 degrees Celsius, when the temperature of the water bait, I'll call it T1, is 30 degrees Celsius, the difference in the height of mercury levels in the two arms of the U-tube is 8 centimeters. The difference in the mercury level is shown as 8. Determine the pressure of the air in centimeters of mercury when the temperature of the water bait becomes 60. Now that the temperature will increase to T2, which is 60 degrees Celsius, determine the pressure of this air and the volume of the trapped air in the gas. They now said when the temperature of the water bait is 60 degrees Celsius and the volume of the trapped air in the glass bulb remains the same, we have to take atmospheric pressure to be equal to 76 centimeters of mercury. The very first thing that we will do is to try to change our temperature so that we don't forget into Kelvin. This should be 303 Kelvin. And this should be 333 Kelvin. We can now find the initial pressure of the air indicated by the manometer. Of course, this is one level, this is another. I always start by showing the lower of the two levels. I'll find its corresponding height in the other arm. That will be B. So by saying that the pressure at A must be equal to the pressure at B, I should be able to get the expressions that will give me those pressures. Now we have air, the whole of this place. So that air will exert a pressure of air. In fact, it's the pressure of that air that I'm looking for. So A, the pressure on air will be the pressure of air. Pressure on B will be the pressure of the two things that you have above B. That is this 8 centimeters of mercury and the atmosphere, P naught. So it will be P naught plus P due to 8 centimeters of mercury. P naught in this case is 76 centimeters of mercury plus 8 centimeters of mercury. If we add that together, we should have 84 centimeters of mercury. That's going to be my first P, my P1. So I know my T1, I know my P1, I want to get I know my T2, and I know my atmospheric pressure. So I can find my P2 using P1 all over T1 is equal to P2 all over T2, which is the statement of the pressures law. My P1 should be 84 centimeters of mercury. All over my T1 is 303. My P2 is the pressure in the second case, that's what they want me to find, and 333. So my P2 should therefore be 333 times 84 all over 303. If we do the answer, if we try to get the answer, we'll have 333 times 84 divided by 303. And that answer is 92 centimeters of mercury. 92.32 centimeters of mercury. And that is our final answer. And with that, we have come to the end of this topic. Join us for another lesson on the physics series. Thank you very much.